Okay, this is Brian, and this week we're talking about nuclear physics. And nuclear physics is related to the material we've been talking about, quantum physics, and it's also related to some things that you've seen before. So we're putting together a bunch of pieces that are familiar to you, but with some new twists. Now, for starters, the thing to know about the nucleus is it's really, really tiny. So here's the size of an atom. It's about 10 to the minus 10th meters. The size of the nucleus is a factor of 10,000 smaller. It's 10 to the minus 14 meters across. And we saw when we looked at the particle in a box that the size of the box changed the energy states. And confining neutrons and protons in the box of the nucleus means that the energies are absolutely enormous. And we're going to do a calculation in class. And if we have particles constrained inside a box that's about 10 ferrometers or 10 femtometers, which is 10 to the minus 15th meters, we're going to look at the particle in a box energy states, and they're on the order of mega electron volts. So not electron volts, but millions of electron volts. And so the energy scales are gigantic for particles in the nucleus. Now I want to remind you of some nuclear accounting that you know of. You know that the number of protons in the nucleus determines the element, and the number of neutrons determines the isotope. That's something you've seen in a previous course. Now, most elements have more than one stable isotope, and for this slide I picked tin because tin has the most number of stable isotopes of any element, all the way from tin 112 up to tin 124. Each one of them has 50 protons in the nucleus. Its atomic number 50. 50 protons, 50 electrons, that's what makes it tin. The number of neutrons can vary from a low of 62 for tin 112 up to a high of 74 for tin 124. Lots of different stable isotopes for tin. Now the number that appears here in the periodic table is the average of all of these things weighted by their abundance in nature. And we will never use that number, ever. Forget that number exists. It is never of interest to us. And when we need to have numbers associated with nuclei, let's take a look and see how we do it. And let's go ahead and take a look at one isotope and talk about the numbers that we'll use and the notation that we'll use. So let's look at uranium-238. Now, uranium-2 is element number 92. It's got 92 protons, 92 electrons. And we put the 92 down here, even though it's basically just, if you know it's uranium, you know it's atomic number 92. You know that that's true. It's a little bit redundant, but it just helps us keep track of things. So we'll typically put that number there. The atomic weight is the number that goes up here, the atomic mass number. It is the sum of the number of protons plus the number of neutrons. It's the total number of nucleons in the nucleus. And so if you're looking for the number of neutrons in this nucleus, it's this top number right here minus the bottom number down here. So the number of neutrons in the nucleus, this particular one's 146. Now, when we're working with nuclei in nuclear physics, you have to know what specific isotope you have. This particular nucleus of uranium-238 has 92 protons and 146 neutrons. It's different than uranium-235, which has 92 protons, but it's got 143 neutrons. That makes it have very different properties. So if you're looking for numbers to use for mass, I'll give you a couple of pointers. First off, never use the atomic weights in the periodic table. Never, ever do that. That is an average over the stable isotopes. It just doesn't make any sense. If we need to do just a rough calculation, we can do this. So if I have chlorine-35, I can say chlorine-35 has a mass of 35 atomic mass units. But when we do energy calculations, that's not good enough. That typically won't work for the calculations we'll do. And in your textbook, you have Appendix C that has atomic and nuclear data. And if we look that up, the mass of a chlorine-35 nucleus is 34.968853 atomic mass units. And we will occasionally need every single one of those digits. Because we're going to do some really accurate calculations, and we're going to be interested in differences between numbers which are very close to each other. So you're always safe to use this. Occasionally it makes sense to use this, but it never makes sense to use that. And in class, we're going to do some exercises that give you a chance to kind of like play around with this notation. I'm sure it's something you're familiar with. We'll look at how many neutrons are in each of the following nuclei. You can do that as a warm-up and do it in class. Now in this chapter, we're going to be mostly interested in unstable, i.e. radioactive isotopes, but there are cases where you're going to be interested in stable isotopes. For instance, if you look at the water that falls as rain and forms ice in places like Greenland and Antarctica, if the climate is warm, there's more oxygen 18 because it's slightly heavier and it just needs a little bit more energy to get up into the atmosphere. If it's cooler, there's less oxygen 18. So if you look at the fraction of oxygen 18 in ice, you can tell basically a measurement of the past climate. You can see here's the years before the present here. Here's the amount of oxygen 18, and there was a spike here 10,000 years before the present or so. That was the end of the last ice age. And so how do we know what temperature it was in the past? This is how we know, and it uses stable isotopes. Now let's talk about what the properties of the nucleus and the physics of the nucleus. And here's kind of an interesting thing. Let's look at a helium nucleus, okay? I got 2 protons right here, and I got 2 neutrons right here. So what holds it together? Because you can see these 2 protons will be pushing each other apart really, really vigorously because they're both positively charged and they're very close to each other. But there is a force called the strong nuclear force that holds together any 2 nucleons. So neutrons attract each other, neutrons attract protons, protons attract protons. Now protons also repel each other because of the electrostatic force, but that is dominated by the strong nuclear force. Now the only problem with the strong nuclear force is it's a short range force, and that has implications for some larger nuclei, as we will see. Now let's take a look at this graph. This is a graph of every single nucleus that's been studied. And on the horizontal axis, we have the number of protons. On the vertical axis, we have the number of neutrons. And each dot is a particular nucleus. You put the number of protons it's got and the number of neutrons it's got, and you make a dot at that spot. Okay? Now, there's only a limited number of the nuclei that are stable. If you draw a line that goes like this, this is a line of equal number of protons and neutrons. Okay? The line of stable nuclei kind of like starts out along that line and then curves upward. So for lightweight nuclei, they have about the same number of protons and neutrons. For instance, oxygen 16, 8 protons and 8 neutrons. Carbon 12, 6 protons and 6 neutrons. Helium 4, 2 protons and 2 neutrons. But as you get to heavier elements, okay, you have to have more neutrons to stabilize them. And it kind of makes sense because the protons are the ones that are repelling each other. You just need more neutrons in the mix to make it go. Now, the strong force that holds the nucleus together only can act over a limited range. And so if nuclei are too big, the Coulomb repulsion is too much, and the nuclei will fall apart. There are no stable nuclei with an atomic number greater than 82. So there's this zone up here where all the nuclei are unstable. And then smaller than that, there's just a limited range of stable nuclei. And if you're above the line of stability, that's too many neutrons. If you're below the line of stability, too few neutrons. And we will see examples of both kinds of nuclei in this chapter. Now let's look at energy levels in the nucleus. And if you draw an energy level diagram for a nucleus, it's similar to the energy level diagram that you would draw for an atom, where you've got different energy levels and you can put in different particles, etc., except the difference is inside the nucleus you've got 2 kinds of particles. You've got neutrons and you've got protons. Let's look at the energy level diagram for lightweight nuclei. Okay, so it gets a little bit more complicated when they get heavier, but if you're putting neutrons and protons in the nucleus, we have an energy level diagram that looks like this. In the energy level diagram, I want to point out a couple of things. One, look at the scale. It's mega electron volts, huge energies. And then if you look at the energy states for the neutrons and the protons, there are distinct states. And you can only put a certain number of particles in each one. So the first state here for the neutrons, 2. First state for the protons, 2. So if you fill them up, you have to obey that rule. And then let's look at filling up the energy levels. So if you take hydrogen, it's atomic number 1. It's got 1 proton. There we go. And then if you look at deuterium, it's got 1 neutron and 1 proton. So I'm going to add a neutron to the mix. And the next stable element is helium. Add 1 more proton. and I add one more neutron, and you can see I filled up this level, and I put in one particle with spin up, and then I put in the next one with spin down, just like you've seen do with electrons. Then you can continue to build up the energy level structure like so. Now we've seen in the electron energy levels for atoms that you can have transitions from higher energy states to lower energy states. And something similar will happen in nuclei, but you have an interesting possibility. Check out this situation. If I'm looking at beryllium-11, beryllium-11 has 7 neutrons, and it's got 4 protons. And they're filled in to the states like so. The neutrons fill it like that, and the protons fill it like this. Now, if this neutron could suddenly change into a proton, there's a room for it in a lower energy state. So if you could switch a neutron into a proton, it could drop into a lower energy state, and this nucleus could go into a lower energy and therefore more stable state. And it turns out it will do that. And what it'll do is one neutron turns into a proton, and so now I have one more proton in the nucleus. So instead of being beryllium 11, now it's boron 11. It's got 5 protons instead of 4 protons. And when it happens inside the nucleus, the neutron turns into a proton and it ejects an electron at a very high speed. And that's the thing we call a beta particle, or a beta minus. It's just a really, really high speed electron. And actually, electrons aren't scary, but this one is scary because it's moving so quickly that it will ionize matter in its path. And that's the radiation that you worry about exposure to. Now, another way that nuclei can decay is if you have nuclei that are just too big and they want to break apart. So if you have uranium-238, it will break apart, and when it breaks apart, a very, very likely piece to break off is an alpha particle. Now, an alpha particle has 2 protons and 2 neutrons. It's basically a helium nucleus, okay? It's a helium nucleus. And so it turns out a helium nucleus, you know, helium is a noble gas. It's got filled kind of electron orbitals. It's also got filled nuclear shells. And so as a consequence, it's very stable in its electron configuration. It's also very stable in terms of its nuclear configuration. And uranium-238 will decay and it will turn into thorium-234. Now take a look at this equation here. We're basically balancing the number of protons and neutrons, okay? So uranium-238, 92 protons, 238 nucleons, throws off 2 protons and a total of 4 nucleons. So what's left over is 90 protons and 234 nucleons. And 234 plus 4 is equal to 238. 90 plus 2 is equal to 92. And so I can basically balance my nuclear equation that way. Now, another type of decay that you can have is gamma decay. And if you have an electron in an excited state, it can drop into a lower state, and it does that by giving off a photon. You can have nucleons in higher energy states, and they drop into lower energy states. And then when they do that, they give off photons, but the photons they give off are really, really, really high energy. They're gamma rays, and they have energies of 1,000,000 electron volts as opposed to a couple of electron volts. And typically the way you do it is you have one atom decay. In this case, we have molybdenum-99 that decays by beta minus decay into technetium-99, and we put an asterisk on it because it's an excited state of technetium, and then it will subsequently decay into the unexcited form of technetium through the emission of a gamma ray. Now in class, we're going to give you some practice working with these different decay modes, and so we're going to ask you to look at determining the daughter nucleus in these cases. And so you can take a look at that, practice up, be ready for doing it in class. We can also look at the parent nucleus and the daughter nucleus, and then you can figure out what decay mode has to be happening to make that true. That's another piece we'll look at in class. The other thing we're going to do is we're going to try our hand at drawing some energy level diagrams, and it turns out boron-12 is a stable isotope of boron. We can sketch an energy level structure for the neutrons and the protons, and then decide what decay mode would you expect, and maybe it's stable, maybe it's not. Stay tuned, and we'll talk about that in class. Now, the big worry with beta particles alpha particles and gamma rays when they're given off by nuclei is that they're really, really high energy. An alpha particle is a helium nucleus, and helium nuclei aren't scary. But when they're traveling at intense speeds, they are, because they're charged particles traveling at really high speeds. They will rip electrons off of atoms. And that's why we say nuclear radiation is ionizing radiation. And it will damage tissue. Okay, this is a radiation burn from a cancer treatment right here. And you can see it just looks like a sunburn, except it's a sunburn that basically goes all the way through. It goes, it can go deep. And that's another thing that's kind of scary about it. But we also use the ionization to detect it in a Geiger counter. And you're going to use a Geiger counter in the lab to detect the radiation emitted by unstable isotopes. Now, the properties of the different kinds of radiation, alpha particles are really, really damaging, but they're not very penetrating. Gamma rays are less damaging, but they're very, very penetrating. Okay, and you can read about that in the textbook. Now, one of the things we want to make a point of when we work with radioactive elements is that radiation is already part of your life. This week in lab, you're going to explore the decay of the progeny produced by the decay of radon. Okay, and it turns out uranium is really ubiquitous in Colorado soils. Like most soils contain some uranium. And uranium-238 is unstable. It's got a really long half-life. It's like 4.5 billion years, but still it will decay. And it decays in this long decay chain. And then when it decays into thorium and protactinium, uranium-234 and thorium and radium, they stay put. If it's in the soil, they're all metals, they're going to stay put. But when it decays and makes radon, the radon will percolate up out of the soil, and it can accumulate in basements of houses and other places. And it's not the radon that's so much of a worry, because it's an alpha emitter, and it's, alpha particles are not that penetrating, so they're not going to get into your body. But the short-lived radon progeny that it produces, those are worrying. And you're going to collect some of those in the lab, and you're going to measure their half-life. And it's amazing. You can run an basically run a blower and harvest dust from the air and end up with a very, very intense radioactive source. And you'll get a chance to take a look at that in the lab. But it's safe. I mean, this is happening all the time. When you're breathing in, you're collecting the same kind of radioactive isotopes. You are being exposed to radiation right now. So we're not exposing you to any extra risk. Now, when radioactive atoms decay, the decay is actually random. And so the nature of the decay is that you have an exponential decay. And we use this equation to express the decay. The number of atoms at some time is equal to the number you started with times 1/2 to the time divided by the half-life. So every half-life, half of the atoms decay. That's the meaning of the half-life. So if I start with a certain number of atoms, n0, after 1 half-life, I've got half. After 2 half-lives, I have a quarter. After 3 half-lives, I have an eighth. Now here's something else to be aware of. There's a couple of things that vary along with the number of atoms. One thing that's going to vary is the activity. One is going to be the concentration, or the number of atoms. But if you're solving problems dealing with radioactive decay, I need some sort of a ratio of an initial number of atoms, of a current number of atoms to an initial number of atoms, or a current activity to an initial activity, or a concentration, etc., etc., some sort of ratio. And we'll look at some examples in class. And the first one we'll look at is the example of Chernobyl cheese. And this is a real story. There was some farmers in Europe after the Chernobyl nuclear reactor accident that had cows who are giving radioactive milk. And what do you do with the radioactive milk? You make cheese out of it, because you're going to age the cheese. And as the cheese sits and ages, the iodine-131 in it would slowly decay away. And actually not that slowly. The half-life is about 8 days. So we're going to go ahead and solve the problem in class and say, how long do we have to store the cheese until it's safe to market? We're also going to look at the use of radioactive atoms to date things. Now, it turns out carbon-14 is produced at a continuous rate in the upper atmosphere, and it also decays at a constant rate. And so the amount of carbon-14 in the atmosphere is essentially constant. So anything living has a certain fraction of carbon-14, okay? And then When something dies, it stops taking up carbon-14. So as things age, they have less and less carbon-14 relative to their carbon-12. And we can use that carbon-14 to carbon-12 ratio to date things. And we'll do an example in class. Now, the activity is the rate of decay, okay? And it turns out if you have more atoms, you're going to have more atoms decaying, okay? And the activity, which is the number of decays per second, is given by this relationship right here. It's 0.693 times the number of atoms divided by the half-life. And I have to put the half-life in seconds in order to have this make sense. And the activity decays exactly the same way that the number of atoms do, because the activity is just proportional to the number of atoms. And the unit we use for decay is a becquerel, and a becquerel is 1 decay per second. And an older unit of activity is one that still gets used. It's called the Curie. 1 Curie is 3.7 times 10 to the 10th becquerels. Why does it have that value? That's something we'll talk about. We'll have a problem we'll solve about that. Now it turns out the wristwatch that I have has hands that glow in the dark, but it's not the kind of glow in the dark that you have to charge up by putting it in sunlight, although you can. This one, the glow is energized by the decay of radioactive tritium, okay? And tritium is an isotope of hydrogen. It's got a half-life of 12 years, and as it decays, it energizes the phosphors of my watch. And so even if my watch has been in the dark, the hands will still glow, and they will glow all night long. They glow with a constant glow. Now it turns out tritium is a beta emitter. It decays by beta minus emission, and it's a very low energy beta particle that does not make it out of the watch. So the radiation dose this exposes me to is 0. There's no radiation dose. But as time goes on, the watch gets less and less bright. And the reason it gets less bright is just because the tritium, which is making the hands glow, has a half-life of 12 years. And I bought it in 2004. And then it had the tritium had an activity of 100 megabecquerels. What is the activity now? That is a problem we will solve in class. Now, something else to be aware of, if you have a short half-life, that means you have a high activity, because the activity is inversely proportional to the half-life. So here's a chunk of plutonium-238, and it is so radioactive that a chunk of it will actually glow red hot. It's kind of crazy. It's just so radioactive. And you can use this particular isotope of plutonium because a chunk of it will get hot and it will stay hot. You can use it to power a spacecraft. So if you have a small sample, you can still get a big count rate. Now check it out. Some of the isotopes you're going to measure in the lab, like lead-214, has a half-life of 26.8 minutes. So a small number of atoms can give you a really, really high activity, and that is something you'll get a chance to compute in the lab. Another thing we're going to look at is this. Some things, when you leave them, they can actually get more radioactive as time goes on. And I'm going to look at, for example, this uranium glass, this Vaseline glass that I showed in class today. I'll bring it back. When it was originally manufactured, it didn't register on a Geiger counter. Now it does. And we'll talk about why that is. We're also going to look at the relative activity of different isotopes of uranium. So take a peek at this problem. This is one we were going to take a look at in class. And then we're going to take a look at the activity, and specifically the units of Curies, and why does it have the name that it does. And we're going to do a series of calculations that allow us to come to a conclusion. And spoiler alert, basically if you have 1 gram of radium-226, it has an activity of 1 Curie. Okay, so that kind of makes sense that you would set it up that way. Now, this equation right here is one you're familiar with. E is equal to mc squared. That means you can convert mass to energy. You can convert energy to mass. And nuclear reactions are so energetic that when they happen, they actually correspond to a decrease in mass. 1 atomic mass unit is equivalent to this much energy. And this equivalence is something we're going to use quite a bit. And I'll show you some examples. we're going to first do something and say, what is the energy needed to make an electron-positron pair? We're going to go ahead and compute that in class. So let's take a look at this situation right here. I'm going to look at a helium atom. Now, a helium atom has a nucleus consisting of 2 neutrons and 2 protons. It's got 2 electrons associated with it. If I broke it into components, there's basically 2 hydrogen atoms, 2 protons with electrons circulating them, and 2 neutrons. The total mass of 2 hydrogen atoms plus 2 neutrons is 4.03298 atomic mass units, but the mass of helium is 4.00260 atomic mass units. It's 0.03038 atomic mass units less. So if you take 2 hydrogen atoms and 2 neutrons and you turn them into 1 helium atom, you get energy out. And the amount of energy you get out is gigantic. That's the binding energy. That's how much you could get if you created a helium, or how much you'd have to put in if you wanted to take it apart. 28.3 mega electron volts, or 7.075 mega electron volts per nucleon. And we're going to do some calculations. For instance, we're going to look at the binding energy for iron 56. And to do that, we have to look up these numbers. And these numbers are in Appendix C in the textbook. So when you have to do these kinds of calculations, you have to use the numbers in Appendix C. We'll also look at nuclear reactions. And it turns out you can fission certain nuclei. Plutonium you can induce it to fission into smaller fragments, and when it does that, it releases a tremendous amount of energy. That's how you make nuclear weapons. So and we're going to take a look at the energetics of that and look at the binding energies per nucleon of plutonium-204 and xenon-133. We will take a look at that, and you can see that if you could take plutonium, a heavy nucleus, and turn it into that lighter nucleus and another lighter nucleus, you can release a tremendous amount of energy. You can also get energy from fusion, and we're going to look at that. And it turns out, if you look at helium-3 and look at its binding energy, it's really small per nucleon. Lithium-6 has a bigger binding energy, so if you take 2 helium-3s, you make a lithium-6, you get a lot of energy out. And we're going to look at the curve of binding energy. And the curve of binding energy has a maximum right at iron 56. So if you have heavier nuclei, you can get energy out by fissioning them. If you have lighter weight nuclei, you can get energy out by fusing them together with other nuclei. And we will talk about that in class. We're also going to talk about radiation dose. Now, radiation damages tissues. We know that's true. And so we want to figure out how much dose is safe. So we're going to use, for a unit of dose, a gray. And a gray is 1 joule per kilogram of absorbed energy. Okay? But we're mostly interested in the dose equivalent, which is the sievert. Now, the dose equivalent is the dose in grays multiplied by the relative biological effectiveness. And it turns out different particles have different cause more or less damage. So X-rays, RBE of 1, alpha particles, RBE of 20. So they basically, if you're exposed to 1 gray of alpha particles, you multiply by 20, that's a dose equivalent of 20 sieverts. And we'll do some examples of calculations like that. Now, every year you get exposed to about 3 millisieverts of radiation. And actually, you probably get a little bit more than that because you live in Colorado. If you get exposed to 350 millisieverts in 1 dose, you're going to experience some symptoms. And if you get 5 sieverts to your whole body, that will kill you. Okay, and so this is probably safe. This clearly isn't. And this is ridiculous. I mean, that's clearly not safe. So whenever we're looking at, is a dose of radiation safe, we're going to compare it to that typical yearly dose. And if it's not much more than that, you're being exposed to a level of radiation that is your body is already naturally exposed to. So we worry less about that than we do with the things that are much bigger. And we do radiation dose calculations. There are 2 different kinds of doses. External, that's stuff that's outside your body, that kind of like the particles that are outside your body, or internal. If you inhale it, you ingest the isotopes. And let's say your natural background is about 7 millisieverts. Certain medical procedures, like a chest x-ray, is about 1/10 of that. So, if you're sick, getting an x-ray, sure, you probably need it, but you don't want to be getting one every day. You want to think about it. And interestingly, taking an airplane exposes you to a lot of radiation for reasons we will talk about. You also get doses from food, but actually the amount you get from food in a typical year is not that great. And the amount you get most from is, interestingly, peanut butter and bananas have a lot. And it has to do with just certain isotopes, primarily potassium. So we'll do some examples of dose calculations and take a look at how to use those. And then we'll talk about airplanes. Why do you get energy flying on airplanes? You get radiation from above. This is data that I took on an airplane. I took out a Geiger counter when we were flying, and I plotted the amount of radiation I was getting, the amount of counts per minute I was seeing as a function of height. And you can see once we got up to elevation, we're getting 350 to 400 counts per minute, whereas on the ground we were getting 10 to 12. So significantly more radiation, and that's from what's called cosmic rays that come from above. And that's why flight attendants get a lot of radiation, because they work a lot of hours a year, and every hour you spend in the air, you are getting exposed to more cosmic rays. Now, a lot of the radiation that you're exposed to, you actually give yourself because of radioactive isotopes in your body. And a lot of it is due to potassium-40. Okay, and we're going to do a little calculation to say, of the radiation dose you get, how much do you give yourself from the potassium-40? And this particular calculation was something that was on a past test problem, so it's kind of a warm-up for that. And finally, we're going to revisit the idea of stability. And if you have nuclei that are too big, you can break them apart. And ones that are too small, you can fuse them together. And particularly the big ones that will break apart, where they will do a chain reaction. And we'll talk about how this works in class. But when people realize that you could do this, they quickly realized that if you could get enough uranium-235 in one place at one time, you can make something that went boom in a fairly major way. And we will spend some time talking about that. We'll also talk about how you can create new elements that never existed before by playing games with the nuclei. And finally, we'll talk about one of the biggest worries about for nuclear accidents or nuclear weapons is the short-lived isotopes that are produced in nuclear explosions are really, really scary. So we'll talk a little bit about that. And we'll also talk about the energy that you can get from fusion. So if I take two hydrogen nuclei, I can fuse them together and make helium. And in principle, you could use that to get abundant, clean energy. The only problem is it's really hard to do because hydrogen nuclei do not want to get anywhere near each other because they're both positively charged. And we will talk about that. And that will wrap up our treatment of nuclear energy. And actually, it will wrap up our treatment of physics, because that's the last topic we'll talk about in Chapter 30. And Chapter 30 is the last topic in the book. And after that, it's all review.